Welcome back to our course, Fundamentals of Operating Systems. Based on the textbook Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter Galvin, published by Wiley Publishing. This unit is on threads and concurrency, so let's begin. A thread is a basic unit of CPU utilization. It comprises a thread ID, a program counter, a register set, and a stack. It shares with other threads belonging to the same process its code section, data section, and other operating system resources such as open files and signals. A traditional process has a single thread of control. If the process has multiple threads of control, it can perform more than one task at a time. This figure illustrates the difference between a single-threaded process and a multi-threaded process. Notice in the multi-threaded process on the right of the image that each thread has its own program counter, stack, and registers, but all three threads are sharing the process's code, data, and resources. Most software applications that run on modern computers and mobile devices are multi-threaded. An application is typically implemented as a separate process with several threads of control. There are any number of types of multi-threaded applications, such as an application that creates photo thumbnails from a collection of images. It may use a separate thread to generate a thumbnail from each separate image. A web browser might have one thread displaying images or text while another thread retrieves data from the network. A word processor, like we mentioned in the last unit, may have a thread for displaying graphics, another thread for responding to keystrokes from the user, and maybe a third thread for performing spell check in the background. Applications can also be designed to leverage processing capabilities on multi-core systems. Such applications can perform several CPU-intensive tasks in parallel across multiple computing cores. In certain situations, a single application may be required to perform several tasks. For example, a web server accepts client requests for web pages, for images, sound, and so forth. A busy web server may have several clients concurrently accessing it. If the web server ran a traditional single-threaded process, it would be able to service only one client at a time, and a client might have to wait a very long time for its request to be serviced. One solution is to have the server run as a single process that accepts requests, and then create a separate process to service that request. In fact, the process creation method was in normal use before threads became commonplace. Process creation, though, is time-consuming and resource-intensive. If the new process will perform the same tasks as the existing process, why incur all that overhead? It's more efficient to use one process that contains multiple threads. If the web server process is multi-threaded, the server will create a separate thread that listens for client requests. When a request is made, rather than creating another process, the server creates a new thread to service the request and resumes listening for additional requests. This is shown in this figure on the screen. Most operating system kernels are typically multi-threaded. As an example, during system boot time on Linux, several kernel threads are created. Each thread performs a specific task, such as managing devices, memory management, or interrupt handling. The command ps-ef that we looked at earlier can be used to display the kernel threads running on a Linux system. Examining the output of this command, one will see the kernel thread kthread-d with a PID of 2, which serves as a parent for all of the kernel threads. One would have a process ID of 1. If you're in my class, why don't you email me with that answer? Many applications can also take advantage of multiple threads, including basic sorting, trees, and graph algorithms. In addition, programmers who solve contemporary CPU-intensive problems in data mining, graphics, and artificial intelligence can leverage the power of modern multi-core systems by designing solutions that run in parallel. The benefits of multi-threaded programming can be broken down into 4 major categories, which I highly recommend that you know. Category 1, responsiveness. Multi-threading an interactive application may allow a program to continue running even if part of it is blocked or is performing some lengthy operation, therefore increasing the responsiveness to the user. This quality is especially useful in designing user interfaces. For example, consider what happens when a user clicks a button that results in the performance of a time-consuming operation. A single-threaded application would be unresponsive to the user until the operation had been completed. On the other hand, if the time-consuming operation is performed in a separate asynchronous thread, the application remains responsive to the user. A second benefit of threading is resource sharing. Processes can share resources only through techniques such as shared memory and message passing. Either of those techniques must be explicitly arranged by the programmer. However, threads share the memory and resources of the process to which they default. The benefit of sharing code and data is that it allows an application to have several different threads of activity within the same address space. That's why I pointed out that graphic to you earlier, showing that all 3 of those threads were sharing the same code, data, and resources. Another benefit is economy. Allocating memory and resources for process creation is expensive. Because threads share the resources of the process to which they belong, it is more economical to create and context switch threads. Gauging the difference in overhead can be difficult, but in general, thread creation consumes less time and memory than process creation. Also, context switching is faster between threads than it is between processes. And the fourth benefit that I want to discuss is scalability. The benefits of multi-threading can be even greater in multiprocessor architecture, where threads may be running in parallel on different processing cores. A single-threaded process can run on only one processor, regardless of how many cores are available. Due to the need for more computing performance, the single CPU systems evolved into multi-CPU systems. Later, designers were able to design multiple computing cores on a single processing chip, where each core appears to be a separate CPU to the operating system. The term parallelism indicates the ability for a system to perform multiple tasks at once. Multicore processors and systems with multiple processors can do that. Multi-threaded programming provides a mechanism for more efficient use of these multiple computing cores and improved concurrency. The term concurrency also suggests the ability to perform multiple tasks at once. However, the term does not necessarily mean multiple cores are at play. Consider an application with 4 threads. On a system with a single computing core, concurrency merely means the execution of threads will be interleaved over time, as shown in this top figure, because the processing core is capable of executing only one thread at a time. Now, we have talked about this several times since the course began, about the fact that a central processor can only process one instruction at a time. And yet, in a multitasking environment, which can in fact run on a single CPU system, we have the sense that we have multiple tasks running all at once. But the fact is, we don't. We may have 4 tasks in operation at any given time, but only one of those tasks has the processor, as we've already discovered. The rest of them are waiting somewhere in one of those queues we talked about in the last unit. It's just that it happens so fast, the switching between one task and the next task and the next task, giving each one their shot at the CPU, is so fast that we have the sense that they're all running at the same time. Surely by this point we all understand that a processor with only one core can only process one instruction at a time. On a system with multiple cores, however, concurrency means that some threads can run in parallel because the system can assign a separate thread to each core, as shown in this bottom figure. Notice the distinction between concurrency and parallelism in this discussion. A concurrent system supports more than one task by allowing all the tasks to make progress. Be thinking as we move through this discussion about our examination of the process manager in the last unit. In this concurrent system on a single core processor, the process manager is swapping out the CPU time between processes and the threads in those processes. Remember the ready queue? The difference is that the operating system maintains a thread control block like the process control block. The operating system saves only the stack pointer and the CPU state at the time of switching between the threads of the same process in the thread control block. Why is there a difference? Well, there's a difference because the thread uses the same memory and other resources as the parent. When the operating system, i.e. the process manager, interrupts the process, all these control blocks, process control blocks and thread control blocks, must be preserved so that they can be restarted later. In contrast, a parallel system can perform more than one task simultaneously. As you can see, it is possible to have concurrency without parallelism. Before the advent of the multiprocessor and multicore architectures, most computer systems had only one single processor, and the CPU schedulers were designed to provide the illusion of parallelism by switching between those processes, thereby allowing each process to make progress. Such processes were running concurrently, but not in parallel. Don't you remember the CPU scheduler, the assistant manager, so to speak, of the process manager? For those of you for whom English is not your first language, please forgive me when I occasionally use these idioms. It's a habit, and I'm sure to let them slip out occasionally. So to speak means to use a manner of speaking or figuratively speaking. The trend toward multi-core systems continues to place pressure on system designers and application programmers to make better use of the multiple computing cores. Designers of operating systems must write scheduling algorithms that use multiple processing cores to allow the parallel execution shown in that last figure. For application programmers, the challenge is to modify existing programs as well as design new programs that are multi-threaded. In general, 5 areas present challenges in programming for multi-core systems. First is the problem of identifying tasks. This involves examining applications to find areas that can be divided into separate concurrent tasks. Ideally, tasks are independent of one another and can run in parallel on individual cores. Also, we have to deal with finding a balance. While identifying tasks that run in parallel, programmers must ensure that the tasks perform equal work of equal value. In some instances, a certain task may not contribute as much value to the overall process as other tasks. Using a separate execution core to run that task may not be worth the cost. Data splitting is a problem. Just as applications are divided into separate tasks, the data accessed and manipulated by the task must be divided to run on separate cores. Also, there is the problem of data dependency. The data accessed by the task must be examined for dependencies between 2 or more tasks. When one task depends on data from another, programmers must ensure that the execution of the task is synchronized to accommodate that data dependency. Also, testing and debugging is a problem. When a program is running in parallel on multiple cores, many different execution paths are possible. Testing and debugging such concurrent programs is inherently more difficult than testing and debugging single-threaded applications. Because of these challenges, many software developers argue that multi-core systems will require an entirely new approach to designing software in the future. Also, many computer science educators believe that software development must be taught with increased emphasis on parallel programming. Let's stop right here and take a break. We're only going to have 2 videos in this unit, and the next video, or the last video, is going to be probably a little bit shorter than this one was. So look over your notes, take care of any business you need to take care of, and when you're ready, come on back and we'll quickly finish with lesson 2 in our discussion of threads.